This dam does not fail where the water first crosses the top. It fails lower down, then the damage walks backward toward the reservoir. At first, the structure still looks enormous and stable. But water is now flowing across material that was never meant to become a spillway. These are AI-generated visuals of a hypothetical embankment dam, not footage of a real failure. The sequence, however, follows mechanisms documented by the United States Bureau of Reclamation and Army Corps of Engineers. Our test structure is a representative zoned embankment. A compacted earth core limits seepage, graded filters and drains control internal water, and rockfill shoulders provide mass and stability. Unlike a single concrete wall, this dam is built from carefully placed zones of soil and rock. Its strength depends on those zones remaining supported, compacted, and connected. The spillway is supposed to carry floodwater safely around or through the dam. Overtopping begins when the reservoir rises above a low part of the crest and finds an unintended route. That can follow inflow beyond available discharge capacity, unavailable gates, debris restricting a spillway, or a settled low spot in the crest. The exact trigger is site-specific. The most important point is this: overtopping usually does not shove an embankment over like a rigid wall. Flow attacks the material that gives the dam its shape. Once water drops across the crest, gravity accelerates it down the downstream slope. Bureau of Reclamation guidance says the most erosive flow is generally here, where velocity is high and particles are easier to dislodge. Vegetation, large rock, or an engineered lining can protect the surface and buy time. But the protection must remain continuous. A single weak patch can concentrate the flow. A bare patch, a change in slope, a material boundary, an obstacle, or uneven vegetation can create local turbulence. That is why damage often begins as one narrow scar, rather than across the entire dam. The first phase can look harmless, shallow sheet flow sliding across the face. Yet it can wash away fine particles, expose rougher material, and make the surface increasingly uneven. Water then collects in the lowest path. A small channel carries more flow, which removes more material, which deepens the channel again. The surface now has a self-reinforcing gully. As the gully deepens, water scours its base. Unsupported soil and rock lose support and fall into the flow, where the fragments can be carried away. The critical feature is a headcut, a steep erosion step inside the channel. Water pours over its edge, scours the base, and causes another piece of the face to collapse. Each collapse relocates that step slightly upstream. Scour, undercut, collapse, repeat. To the eye, the whole seems to climb uphill, even though the water itself is still moving down the slope. Cohesive soil often fails in blocks as a headcut advances. Looser, cohesionless material may erode more uniformly at first, but an irregularity can still develop into a moving headcut. A badly eroded downstream face is not automatically an open breach. Bureau guidance distinguishes this initiation phase from breach formation. The reservoir remains separated until erosion reaches and cuts through the crest. That is the dangerous direction. A headcut can begin near the downstream toe or edge, progress up the slope, and finally reach the top of the embankment. Once the retreating edge reaches the crest, stored reservoir water connects directly to the eroded channel. The failure has entered a faster and far more dangerous stage. A deeper or wider opening passes more water. More water can remove material faster, which enlarges the opening again. The breach can widen and deepen while the reservoir level begins to fall. Heavy rock armor matters. Large, interlocked stones are harder to move and can shield finer soil below. That can delay surface erosion compared with an unprotected earth face. But armor is not magic. If turbulence removes smaller material beneath it, or a headcut undercuts its base, the stones lose support, tumble into the channel, and expose a new surface. So how long does failure take? There is no universal stopwatch. The depth and duration of overtopping combined with how erodible the embankment is are key parameters. Material type, compaction, zoning, vegetation, armor, crest profile, flow concentration, and the condition of the spillway all change the outcome. Small geometric details can control where the first gully forms. Some dams and levees have survived shallow overtopping without breaching, other structures have failed quickly. These visuals explain a credible mechanism, but they cannot predict a real dam's time to failure. Our verdict is red for prolonged, concentrated overtopping of an unprotected or compromised embankment. It may remain standing at first, but once headcutting reaches the crest, survival becomes increasingly unlikely. The dam is not necessarily defeated by one enormous push. It can be dismantled piece by piece, from downstream to upstream. In extreme engineering, the smallest new flow path can decide the fate of the largest structure.